Chemistry unit 21, theory video 5. We are going to look at buffer solutions. So a buffer solution is something is a solution in which the pH would not change very much when small amounts of acids or alkalis are added. So that means it is used to buffer solutions are used to maintain the pH value at a constant level. So this buffer solution is going to be either an acid and its conjugate base, or a weak base and its conjugate acid. So it is going to be either a weak acid and its conjugate base, or a weak base and its conjugate acid. So this will actually not change the pH when acid or alkali is added. So now when a weak acid is and one of its salts is taken, that can act as a buffer solution. For example, if you have ethanoic acid and sodium ethanoate, if you add them in different proportions, they will act as buffers between pH values of 4 to 7. So these buffer solutions work based on the equilibrium that we take into consideration. So now what happens is, when ethanoic acid is added, it dissociates. Some of its molecules will dissociate to H plus and CH3COO minus. So then you have a low concentration of ethanoate ions in the solution. When you add sodium ethanoate, it actually fully ionized. It gets fully ionized into aqueous solution. So CH3COO Na is there, that dissociates into Na plus and CH3COO minus aqueous ion. So as you can see, in both of the acid and the salt, CH3COO minus, that is ethanoate ion, is going to be common. So that means the CH3COO minus ion concentration is going to be higher. So we say that there is a reserve of ethanoate ions. This reserve supply of the acid, because most of the acid is not dissociated because it's a weak acid, and there is a reserve supply of CH3COO because it is coming not only from the acid but also from the salt. So the pH of the buffer depends on the H plus ion concentration only. The pH depends on the H plus ion concentration, or in other words, it depends on the ratio of the concentration of the acid and the concentration of its conjugate base. So if that does not change, the pH would not change very much. So what happens is, you have relatively high concentration of ethanoic acid is there because ethanoic acid is not dissociated fully. Then you have relatively high concentration of ethanoate ions because you have got it from sodium ethanoate as well. So then if you increase the hydrogen ion concentration, the H plus ion concentration, if there is more H plus ions, so that means it would lower the pH value. So if you add H plus ion, what would happen is, it would join together with CH3COO ions to form more CH3COOH until equilibrium is re-established. Because it is going to shift the position of equilibrium to the left, because there will be more H plus. So because of the large supply of CH3COO minus from both sodium ethanoate and acid, it ensures that the CH3COO minus ions concentration would not change that much. Then at the same time, CH3COOH, there is a lot of CH3COOH. So because that concentration is high, the newly formed CH3COOH, there wouldn't be a significant impact on the number of ethanoic acid molecules. So as a result, pH does not change much. Or in other words, what you can understand is, because of this, the introduced H plus will join with CH3COO minus ions to produce ethanoate ions, to produce ethanoic acid. So because they don't dissociate much, what will happen is the pH does not change. So that is what happens when you add H plus ions. When you add hydroxide ion concentration, or when you add hydroxide ions into this, the pH would be increased. But if you add it to a buffer solution, what would happen? The H plus ions in the solution will join with OH minus ions to form water. So that would reduce the H plus ion concentration and the equilibrium shift to the right. So then what happens is, when there is less H plus ion, more CH3COOH will break down to produce more H plus and CH3COO minus ions to form the equilibrium again. Because there is more CH3COOH, the concentration does not change that much. Then again, the large supply of CH3COO minus will make sure that the CH3COO minus concentration does not change significantly. As a result, pH does not change significantly. I hope that makes sense. So now, in unpolluted regions of the earth, rainwater has a pH of 5.7 because carbon dioxide is dissolved in rainwater and that produces carbonic acid H2CO3. So it has its conjugate base HCO3 ion, and which is going to act as a buffer solution. So if small amount of acids and alkalis are added to the rainwater, there wouldn't be much change in the pH value. But if you take a region where acidic oxides, or the acidic oxides of nitrogen and sulfur are present because of pollution, the pH would fall to about 4. Because the carbonic acid and the HCO3 bicarbonate ions, they are not enough in concentration to cope with the large amount of acid that is added to the rainwater because of the pollution. So you must understand that it is only small amounts of acids that we talk about. So it is not about large acids, large amounts of acids, because if you add large amounts of acids, then of acids or bases, then the pH will change significantly. Now, if you take in alkaline regions, if you want to resist changes in the pH of alkaline regions, it is usually a weak base and its conjugate acid. For example, like ammonia and ammonium chloride. So then ammonia plus water give you NH4 plus OH minus, and NH4Cl dissociates into NH4 plus Cl minus. So NH4 plus is going to be the conjugate, the reserve supply of the conjugate acid NH4 plus will be defined by that, because it is a proton donor. I hope it makes sense to you. Write down buffer solutions. A buffer solution maintains, and I can remember that I have taught you this lesson before. Buffer solutions maintain its pH without letting it change significantly when small amounts of acids or alkalis added. Leave line and write. Usually for acid pH values, buffer solution is a mixture of a weak acid and its conjugate base, for alkaline, for alkali pH values, it is usually a weak base and its conjugate acid. For example, ethanoic acid and sodium ethanoate. Leave a line and write. CH3COOH, that is ethanoic acid, is a weak acid, so dissociates only partially. And write down the equation. CH3COOH, aqueous, reversible sign H++, CH3COO minus aqueous, that is ethanoate ion. Sodium ethanoate is fully ionized in aqueous solution. CH3COO solid plus aqueous gives you Na plus aqueous plus CH3COO aqueous. Because there is a reserve supply of both the acid CH3COOH and its conjugate base CH3COO minus, their ratio will define the pH value. If it does not change, pH remains the same. That means, in other words, the H plus ion concentration is what defines this thing, because when CH3COOH breaks up, it produces H plus ions. So if it breaks up, there will be more CH3COO minus. So here what happens is they both remain the same. When H plus ions are added to the buffer solution, equilibrium shifts to the left. And more H plus ions combine with CH3COO minus to form ethanoic acid. Please write down this equation. Because of the large reserve supply of CH3COO minus within brackets, both from the acid and sodium ethanoate, the CH3COO minus concentration does not change significantly. Next one, the large reserve supply of CH3COOH ensures that the CH3COOH molecule concentration does not change significantly. As a result, pH does not change significantly. For OH ions, the same thing happens, where OH ions combine with H plus ions to form water, reducing the H plus ion concentration. As a result, equilibrium shifts to the right. More ethanol breaks down to form ethanoate ions and H plus until equilibrium is reached. Large supply of ethanoic acid and ethanoate ions ensures their concentrations remain the same. As a result, pH does not change. Leave a line, put a star and write down. For a buffer solution to function, only small amounts of acids or bases needs to be added. If excess acid or base is added, pH will change rapidly and more. So if you want to, please do question number 8. If you have any doubts, please raise questions. If we are to calculate the pH of a buffer solution, we need two things. We need the Ka of the weak acid and the equilibrium concentration of the weak acid and its conjugate base, that is the salt. So now, for example, if we take the ethanoic and ethanoate ion concentrations, so we would need the concentration of the acid as well as the salt concentration. Both of them are required. So here H plus ion concentration is going to be Ka multiplied by acid concentration divided by salt concentration, then which we can write as pH is equal to pKa plus negative logarithm of the salt concentration over acid concentration to the base 10. I hope that makes sense. Please write down. When calculating the pH of a buffer solution, we require the Ka of the weak acid, equilibrium concentration of the weak acid and its conjugate base. Write down the equation. H plus ion concentration is equal to Ka into acid concentration upon salt concentration, which can be written as pH is equal to pKa value plus logarithm of salt concentration upon acid concentration to the base 10. These two equations. If you have any doubts about how these two expressions are taken, please ask me, then I will explain it further. So I hope this makes sense. Please do question number 9, 10, 9 and 10. Let's look at this worked example 6 before you go to the questions. Calculate the pH of a buffer solution containing 0.6 mole per cubic decimeter propanoic acid and 0.8 mole per cubic decimeter sodium propanate. It's quite easy. Then they would give you the Ka of propanoic acid, 1.35 × 10 to the power minus 5 mole per cubic decimeter. So we write the equilibrium expression. Ka is H plus ion concentration into C2H5COO minus concentration again over propanoic acid concentration. So we take the H plus ion concentration is equal to Ka multiplied by the acid concentration over ion concentration as seen here. Ka, this equation is what we have obtained. It is the same thing. Now you understand how we reach that equation. Then we can the ratio determining H plus, that is in turn the pH, is the ratio of the concentration of the acid to the salt, that is the conjugate base. That pair is what defines the concentration. So we substitute the values, we get the H plus ion concentration to be 1.01 × 10 to the power minus 5. Then we calculate the pH by taking the negative logarithm to the base 10. I hope you understood. If you understand, please do the questions 9 and 10. In the next video, we will go to the uses of buffer solutions.